All right. Hello, everyone. My name is Jonathan Chambers, and this is Josh Peterson. We're two members of Unity's scripting team. And for about the past 2-3 years, we've been working on IL2CPP, which is what we're going to talk about today. So for today, just to go over what we're going to talk about, one of the pillars in the Unity keynote we talked about was solving hard problems. And IL2CPP seeks to solve those hard problems for you. We're going to go a little bit in depth today. If you've heard the 80-20 rule, this is more like the 99-1 rule. So 99% of the time, you're really not going to care what we talk about today, because hopefully IL2CPP works, IL2CPP runs fast, and there's nothing you have to do on your side to solve these problems. But for that 1% case where you maybe have a bug, or maybe the performance isn't what you're expecting, the things we're going to go over give you a little bit of insight into how to solve that. So first, I'm going to give a brief overview of what IL2CPP is, for anybody who doesn't know. Then Josh is going to talk a little bit about how we built IL2CPP. And then we're going to do 2 deep dives, one into debugging and one into profiling IL2CPP. So how many here know what IL2CPP is? OK, so most of you do. So for these that don't, I'm not going to give an in-depth discussion of IL2CPP. There's 2 talks out there on the internet at Unity's website. One I gave at Unite last year, and one Lucas and Ralph, 2 other people who work on scripting, gave at Unite Amsterdam. And that gives a nice deep dive into what IL2CPP is, why it came about, and how it works. But IL2CPP came about 2 or 3 years ago. We had some issues we were trying to solve. One of those issues was WebGL was in its infancy, and we were trying to figure out how we were going to run user scripts in the browser. So the browser obviously executes JavaScript, and we couldn't use the standard mono runtime that we normally use to run your code. So we were sort of brainstorming about how we were going to make this code run in the browser. At the same time, we were porting to a lot of platforms, and what we were noticing was that our ports to the mono runtime were taking a long time. It was taking 6 to 9 months or more to get something up and running and bootstrapped, and it took even longer to get it performing where we wanted it to be. And we were trying to think of better ways that we could port faster and move quicker within Unity. These 2 groups sort of got together and had a brainstorm and said, you know, when we port the Unity runtime or when we run the Unity runtime in WebGL, we just compile the engine down, the C++ code. And what we thought was if we could somehow get your user scripts, get your assemblies into C++, we could then compile it with the native platform compiler, and it would run on whatever target we were targeting, whether it was the browser or any of these new platforms, just as easy as the engine could do. And that's sort of where IL2CPP comes in. It's a tool that takes your user scripts, your assemblies, the code you want to run, it converts it to C++ source files. We then compile it with the native platform compilers, and then just run that code on the target device. This allows you to do a couple nice things. One is it keeps you guys in the same tools you like today. So if you like using Visual Studio and ReSharper, you don't have to learn a new programming language. You don't have to learn a new IDE. The way you go about making your game doesn't change at all. So we've plugged IL2CPP into Unity, and the way you go about authoring your game hasn't changed at all. A couple of the nice things is it solves the problems we were looking at, though. So we can port a lot faster when we do ports for IL2CPP. A lot of them underway right now. We're looking at 1 week to 2 weeks to get something up and running our test suites and passing. So obviously going from that 1 to 2 weeks from a year or more is great for us. We've also had the added benefit of, by leveraging the platform compilers, we're getting great performance out of IL2CPP. So you're usually seeing a nice speed boost by running IL2CPP with your content than the previous runtime we were using within Unity. Where IL2CPP is today, it's on WebGL and iOS at the moment. At 5.2, we released previews for Android, for Xbox One, and for PlayStation 4, and we're continually bringing it to the remaining platforms that we have. So I've told you a little bit about what IL2CPP is. Josh is going to talk to you now about how we go about building it to meet the goals we have for it.
Thanks, John. So not only do we want to tell you how we build IL2CPP, but really want to tell you why we build it that way. And that's probably the most important thing, and maybe the most important part of this talk. So I thought that we could probably sum up the way we build IL2CPP in 1 slide. So we've got about 55 minutes left. Are there any questions? No, that's not actually how we build it. Our team is not quite that big. My favorite one is the guy in the back with the face palm. I don't know if you can see him. Like we've all had moments like that, maybe more than we like to admit, right? So in truth, one of the things we tried to do when we set out to build IL2CPP is prevent moments like that, right? We want to make sure that our runtime works the way we expect it. So our team is really focused on test-first development and test-driven design practices. Up here, you can see some metrics for the number of tests we run on the IL2CPP code only. And specifically, we have a lot of integration tests. Those are end-to-end tests. They compile or convert an assembly from C# or IL into C++, compile the C++, run the executable, and compare against Mono or .NET. So that really tests the full kind of IL2CPP tool chain. And those integration tests are not maybe as fast as unit tests are, but we use them because it helps us to refactor things behind the scenes. So we can change code generation, we can improve the runtime, and we can make sure that we don't regress in the things that we ship. Because it's really important for us, like John mentioned, that you shouldn't really care a whole lot. This should just work. And we also like to run a lot of platform integration tests. These are tests that verify the behavior of the Unity editor and the Unity runtime all the way down through the scripting backend. And our platform teams can use these as their porting to get a good feel for how well their platform port is going. Once all those tests are green, we know that we have a good base that we can move forward with. Now, on the tools side, first of all, the languages we use, our code conversion utility is IL2CPP.exe. It's all written entirely in C#. And we'll talk about why we made that choice a little bit later. And the runtime, which we call libIL2CPP, is written in C++ code. And one of the nice things is we've got C++ compilers for all of our platforms, right? So we can easily compile this across all the platforms we need to. It's written to the C++ 98 standard. But in addition to shipping on multiple platforms, we also develop on multiple platforms. So we use Visual Studio and ReSharper on Windows. We really like C# at Unity, if you haven't noticed. We really like ReSharper. All of those tests run inside an NUnit test runner. So ReSharper's integration is really nice on OS X. We make use of the Xamarin Studio and Xcode. And one of the real nice benefits of having both the generated code and the runtime code in C++ is we can use the nice profiling tools we've got on various platforms. So one of our biggest platforms for IL2CPP is iOS. So we use instruments on a regular basis to profile our code, to profile projects that we get as we're looking to improve performance. But we've also built a few custom tools that we use. We have IL2CPP on standalone players, PC and Mac. And we use that internally for debugging, which is really nice. In the talk at Unite Amsterdam, Ralph and Lucas discussed this on the feasibility of releasing it. It's going to be released at some point. We don't quite know when that is. We've got some issues around tool chains for development builds and cross-compiling we need to sort out. But at some point, we'll be releasing that. We also spent a lot of time early in IL2CPP improving the build size. For those of you who are early adopters, you knew that the original builds were too big. And we're really happy to report that we're now at the same build sizes as the monoscripting backend, even smaller in a lot of cases. And so we wanted to make sure we didn't regress there. So we built some internal tools that compare our code conversion with real-world projects and asset store bundles for build time and build size. Of course, build time is our biggest issue we're facing right now, and the thing that in the near term we're most working on for developing on the IL2CPP scripting backend. One of the nice things we've done is built a profiler into our code conversion utility so we can see where the time is going. But in addition to these tools, we also chose to lay out the runtime code in a way that I think makes a lot of sense to meet our goals. So I wanted to spend a few minutes taking a look at this kind of block diagram of our runtime code layout. Now on the left, there's two entry points. You can come in through internal calls, or ICalls, which are managed to native calls that come from the system libraries like MS Corelib or from the engine code. And of course, we can come in from the generated code, your script code or assemblies in your project that we've converted. Both those call into a virtual machine, the VM layer, that provides a nice interface for all of the services that the VM provides. I think of things like files, directories, locks, threads, garbage collection. And that VM then calls into a really thin platform abstraction layer, the PAL. That's where we have common types for things we get from the OS. Like, for instance, all our operating systems have to provide a wait handle. So we have a common type for a wait handle in the PAL, and the VM can communicate only with that wait handle type. We don't have to worry about the specific ones for the different OSs. And then on the far right of the diagram are the various platform ports. And that's where our porting teams come in. iOS and POSIX, Windows, other platforms we've released, some we're still working on, some that don't even exist yet. When we take a look at the amount of code in the runtime, the stuff on the right is actually really small compared to the stuff on the left. So our platform teams just focus on a small segment of the code where they can really take their areas of expertise, understanding the native APIs and the specific performance issues on a platform, and apply them. So that also helps us because when we make changes, we fix bugs, improve performance on the left side of the diagram in the VM and the way we generate code, that's available for all platforms immediately. So this layout's really helped us to ship new platforms, like John said, much more quickly than we could with the monoscripting backend, which is one thing we really like. So we've talked a bit about how we're doing this, but really, like I said, the important thing is why we're doing this. And our goal, our single goal with IL2CPP, is to move fast, right? We want to move fast because we want to have the best converted code. We wrote our code conversion utility in C# for developer productivity. We have some great profiling tools that we can use because we have everything in C++ now, so we can use tools on the machines. And our porting teams can port things quickly because of the way we've laid things out. And our goal is to be able to iterate quickly with IL2CPP to provide you with the best scripting backend that we possibly can. But maybe more important than us moving fast is we want you to be able to move fast in your development, right? And sometimes moving fast is not so much about checking in code quickly and iterating, but it's about solving a really hard problem that might be blocking your team. So I'm going to talk for a few minutes about how we can debug script code with IL2CPP. And the first really answer to how to do that is simply to not do it. The best option for debugging script code is still in a code editor. At 5.2, we shipped the really nice integration with Visual Studio. If you're working on Windows, debug your script code there. It's great. We've got MonoDevelop, of course. At 5.3, you saw we're shipping a new version of MonoDevelop, and we're going to have a better roadmap going forward to upgrade MonoDevelop. So there's going to be nice tools on both OS X and Windows platforms. You can still debug with the Mono scripting backend on your device if you want to do that. Even for iOS, where we can't ship on the App Store, we can use the Mono scripting backend locally for script debugging. But if you're like me, the most fun option is definitely debugging the generated C++ code. Right? OK, so maybe you don't all enjoy debugging generated code like I do, but it is useful in a few cases. So maybe you've got an exception on your device. It only occurs there. Maybe it only occurs on this scripting backend, right? You have to debug it there. Maybe you're interacting with native code, and it's nice to see on the call stack how you're being called from the managed code. And we can see that now with IL2CPP because we're generating all that in C++. Or we've all done it right. We've written marshalling code. And we've done it wrong the first time, and the second time, and the third time if you're me, usually. With IL2CPP, we're actually generating code for all those marshalling directives. So we can step through them in the debugger, see where our problems are, look for performance bottlenecks because we're allocating code we shouldn't be. It comes in really handy in those cases. So I'm going to go ahead and do a demo here and see how we can actually do this. OK. So I've got Unity up here with this project I've been working on. This is a new game I'm developing. It's about 90% done. This is my opening scene. And the idea here is we can click on one of these heroes, so the Nightmares hero, and we get to see which boss they'll fight at the end of the level. So it's the Zombunnies. And for the blacksmith, we got this unwanted visitor here. You get the picture, right? So if we look at the script code, this is my boss selector script, my mono behavior. And this is the one that does all the work. So I've got 4 fields here. One where we have the name of the hero, who the user clicked on, and then sprites for each of the bosses. When you click on each of the heroes, we'll set their name. And then every frame, we just call this getBossSprite method if we've got a hero set. And we look up and find the correct hero. Pretty straightforward. It's a contrived example, but I think it'll work for the demo. So I've got it running on a device here. I'm going to go ahead and bring up Xcode. And let me zoom in a bit. OK. So I've got it running on my iPad here. And I can click on the various heroes just like you saw me doing. I'm going to click on UnityChan. And you can see we've got an exception here. OK, so I'll click off UnityChan for a moment. And let's take a look at this exception. It's telling us that we've not found a boss for UnityChan. OK, and then notice that we're in the getBossSprite method inside update, so we've got a problem. Now, right now, if you're debugging this in the real world, right, you want to go to a code editor, Visual Studio, MonoDevelop, right? There's no reason to debug this on the device. But just for purposes of the demo, let's go through the exercise of debugging this in Xcode, in the generated code, so you can see how it works. So the first thing I like to do when I hit a managed exception is in Xcode, I can choose debug and then breakpoints. And I can actually create an exception breakpoint here. And in IL2CPP, we wrap all of the managed exceptions with C++ exceptions. So if I want to really filter down and only pick up the exceptions that IL2CPP is throwing for managed exceptions, I can use this IL2CPP exception wrapper type. And now what I should see in Xcode is I should break whenever I hit UnityChan. Let's try it. And there it is. So I'm going to zoom in a little bit more, hopefully give you a better view. This is the call stack that we get at the exception. Notice at the top here we're in a couple of inline methods that don't matter. But as we go down through the call stack, we can see here we're in the VM raise exception call. This is that VM block in the block diagram of the runtime. And here we're in a codegen raise exception call. And then here, this next frame is the one that really matters. This is our converted script code for that getBossSprite method that I showed you earlier, right? And you can tell that because here we've got the name of the class, boss selector. GetBossSprite is the method name. And then this underbar m indicates that it's a method. That's our suffix for a method when we generate code. And then 5 is just a number that we increment as we build all the methods. And you can also look down on the call stack and see that we're in the update method. And even down here, we're looking at some of the calls in the Unity engine, player loop, common update. We can't see the code in here, but it gives us a nice sense of where we might be in the code. All right, so let's go take a look at the code in GetBossSprite over here in Xcode. So the first thing to notice when we're taking a look at this generated code is it doesn't look anything like our C# code, really. So remember that we're converting the IL, not the C# code. So keep that in mind, and some of the names can help you get your bearings a little bit. OK, so the getBossSprite method here has one argument, which is this. So it has no arguments in C#, but this argument we pass in. Let's go and inspect what the actual boss selector looks like. So down here at the bottom on the Xcode window, I can expand out this just like I would any other native code in Xcode. And I can see that I've got 4 fields here corresponding to the 4 fields in the boss selector class. Now, notice that we prefix these fields with these underbar characters. That helps us to avoid naming conflicts when we generate the code. But for me, when I'm reading these in my mind, I can't read underbar, underbar, hero, underbar 2. I can't say that in my mind enough. It drives me crazy. So you have to kind of build a mental filter when you're looking at generated code to kind of remove those underbars. This is just the hero field. You can say that. The hero field is of type string, and we've got these 3 sprite types. So let's expand the hero field and see if we can determine what the actual value of the hero is that we're setting here in the boss selector. So at first glance, this doesn't look anything like a string, right? Our display of in Xcode is not that good. So what we're going to need to do is take a look at the way a string type is actually laid out in native code when we generate it. So to do that in Xcode, I can open up this file that's object_internals.h. Object internals. This file actually ships with your Unity install. If you have any Unity install with IL2CPP, you've got it in there. You can inspect it yourself. And in this file, there's some of the information about how we lay things out in native code. So this IL2CPP string struct is actually the real native type that we use for a system.string. Every managed object in IL2CPP has this header, IL2CPP object. And then the string has a length, a 32-bit integer, and this sort of odd array of characters. In IL2CPP, we're representing all characters, or all strings, as a sequence of 2-byte UTF-16 encoded characters. And this zero-length array defined is actually the number literal 0. So what happens here is we have this struct that we lay out first in memory, and then we put all the characters after it. So this chars array looks to the compiler and the debugger like it's an array of 16-bit characters, basically. And that's how we'll use it. OK, so let's go back to the source code, and then I'm going to go down to my window here in Xcode. So another thing I like to do when I'm debugging generated code is sanity check myself often. Because you're in unfamiliar code you didn't really write, sometimes it's easy to get lost. So a nice thing to do is take a look at this object header. This is the IL2CPP object we saw in that IL2CPP string type. There's a type info pointer in here, which has a lot of great information about the type we're dealing with. So we can see in the namespace, this is a system, and the type is string. We're in a system.string. That's what we expect, right? So that's great. We're in the right place. And we know the length is 9. OK. And the start char 1 corresponds to that chars array, but it's just showing us one uint16. So to see the string, we can actually go to the LLDB prompt and put together this relatively horrible incantation. One thing we're looking at from a development perspective is improving kind of this native debugging experience. So I'm hoping soon to have some better utilities that we can provide. But for now, we can use this stringutils class. There's a stringutils.h header that also ships with your install, which has a function we can call. It's called UTF-16 to UTF-8. And this will convert an array of UTF-16 characters, how we're storing our string, to a nice UTF-8 string, which Xcode can display. So what I'm going to do is pass to this this, and Xcode should help us out here, hero. Good. I'm going to cast this to the IL2CPP string type that we saw. And it's IL2CPP string pointer. And then if I use one more set of parentheses here, Xcode should help us with that type, and we can want the chars. And if I do that, we'll see that, great. Our hero is UnityChan. I clicked on UnityChan. That's what we wanted. That was really hard to get to that point, right? You see why you want to use a code editor when you can. OK. Now, so we know that UnityChan is is our hero. And I'm just going to step through this code now. So like any other generated code, any other native code in Xcode, I can set a breakpoint right here. And I'll just let it run. And the next frame, I should hit it. OK. So I'm just going to step over with F6 in Xcode. And here I get to string op equality. So this is a method in the MS core lib, string equality, right? We're comparing L0, which we can see from this line just above, is our hero. So that's Unity Chan. And with string literal 2. So let's do the same kind of thing. I can just go down here with my magic incantation in LLDB. Thankfully, I can use up, so I don't have to type it all again. And do underbar string literal 2. What was that? Blacksmith. OK. So Unity Chan is clearly not equal to blacksmith, right? We know that. So we should step over this. And oh, I hit the wrong one. Excuse me. There we go. OK, sorry, I'm back at my original breakpoint. I apologize. There we go. So we'll step over, and L1 is false, right? Good. Unity Chan is not equal to blacksmith, exactly what we expect. So I can continue to step here, and we do another comparison. Now we're comparing with string literal 1. L3 is, again, our hero. That's Unity Chan. So string literal 1. And let's see. I should be able to go here. And nightmares. OK, that's the nightmares hero. And we know that that's not going to be equal, so we'll step over. And false. Great. And so now we should compare against Unity Chan. But OK, here's the problem. Notice that we're in a block here. We're not going to exit. And we're going to raise our exception. So you probably all know what the problem is, right? My code is not so good, and I've missed a case. So I'm going to go back to, let me zoom back out. OK, so if I go back here, I'm going to need to add a case for Unity Chan, right? So that's pretty easy to add. And I think my project is about 95% done. And I'm nearly ready to ship back to my customer now. Unity Chan boss. We'll save that. And you might be wondering who Unity Chan's nemesis is, right? So let's run it and see. Yes, Dr. Charles. OK, so I wanted to switch back here and just kind of mention a few of the principles that we use and I talked about when we were debugging that generated code. So first of all, this is not C# code. We're looking at IL. I like to use a tool like IL2CPP to convert my assemblies to IL and then kind of see what it looks like there to better understand the generated code to get my bearings. Second, filtering those underscores, at least for me, is really important. I say the names of the types and the names of the fields in my heads, and I need to be able to kind of build that mental filter. I think it's a good skill to have. And sanity check yourself often. Look at that type info pointer. Look around the code to make sure you're in the place you think you are. Finally, understanding those type layouts, the way that we're laying out the managed types in native code in that object internals header is really helpful, especially for the cases like when we don't have the nice debugging helpers. That's really nice. So, all right, you've seen all this, and some people might be a little bit scared right now. So the question is it really a good idea to do this? Most of the time, it's not a good idea to debug the generated code, right? You need to watch out for a few things. We're going to change the generated code in newer versions. We're always looking for better ways to improve the performance, both build time and run time of generated code. So it's going to be similar, but it will change. And in a real-world project, we're generating a lot of C++ code. If you've looked in the IL2CPP output directory, there's a ton there. A lot of times, Xcode just can't handle that really well. But there's certain cases where this is really an important skill to have. So I encourage you, if you get some time, give it a try. Play around with code that you know. And then if you get into a situation where you've got a tough bug and you need to get into the generated code, there's more information here than we have with the monoscripting backend. So it is possible to debug, and it's a nice skill to have. Now, if you're interested in more information about this debugging, we have a blog post series where we go through a lot of this kind of stuff. And specifically, there's one entry there on how to do debugging generated code. So it's a nice place to look for more information. Well, now that we've got your code correct, it's important that we make it fast. And John's going to talk to us next about how to do some profiling.
All right. Everybody awake? It was like after lunch, and then we're looking like it's C++ code, and everybody's kind of like dozing off now here. All right, so I'm going to talk about performance and profiling out of CPP a little bit. And before I do that, I want to give a word of caution. right? So I can see like as soon as I say the word that X is faster than Y, like someone's just like sitting in their chair ready to jump up and like tell me I'm wrong. So we're going to have some like general advice, and then I'm going to give some very specific benchmarks. So by that I mean you'll see when we go through these examples, I'm running a certain set of code on a specific device compiled by a certain compiler, and we're making a lot of changes to IL2CPP, so that code may get faster. Sometimes it gets slower. There's also some comparisons to our current version of Mono, which is not the newest version of Mono that's shipping. So all this is basically a snapshot in time and how something was run. I want to give you guys an insight how to do the profiling, not exactly a set of things you must do to get fast code. So all that said, as I said at the beginning of the talk, the good news is we're doing almost all this for you. So we do that by generating the C++ code that Josh just showed you. And what happens is when we generate that C++ code, we compile it with the optimized platform compilers for the platform you're targeting. And we're leveraging basically human decades or human centuries of effort that have gone to make those compilers robust and fast for those platforms. So we're not trying to reinvent it ourselves, whereas before, we basically were trying to do our own optimizing compiler to take your IL into native machine code for every one of the platforms and architectures we were supporting. We're also making this better. So IL2CPP, if you've noticed, has fixes in almost every patch release and also rolls up into the larger releases. And what that means is with all the tools we have for profiling ourselves, we're making it incrementally faster at pretty much every release that's coming out, both for build time and runtime. Another thing for performance is we're not just talking about speed here. We're also talking about size. Size both of your deployment and also of your runtime memory. With deployment, we put a lot of work in, especially at the beginning of IL2CPP. In the past, when you were targeting mobile devices, you had the option to basically strip bytecode if you've seen that before. With IL2CPP, that's always enabled. We wrote a new logic to actually do a static analysis on your code and remove anything that we can prove you're not going to actually call in your deployment. Another thing we did was, since we're leveraging tools like Clang, we can take advantage of any optimizations it has for reducing size. So on iOS now, when you're targeting 32-bit, we actually enable the thumb instruction set, since it's just a switch we can throw on the compiler, and we were seeing that reduce binary sizes, 20% or 30% of deployed binaries in 32-bit mode. As for runtime memory, that's also something we were very careful with. When we initially did IL2CPP, one of the things we thought about doing was sort of generating as much information ahead of time as possible, and what it turns out is that for deployment size, that was bad. For runtime memory, we also thought about generating as much as possible, and that also affected runtime memory. So we were loading too much into memory at startup, and what we do now is we make things much more lazy. We take the assemblies that deploy into your project. At build time, we actually extract all the metadata we need. So when we do the conversion, we actually convert the code, which was the C++ you saw, and we also extract all the metadata, the types, the methods, the fields, the properties, and we re-encode that into a binary blob that we store on disk. That's an external file, so on platforms like iOS that are multi-arch, that means we're only shipping that data once. When we first were starting with IL2CPP, we actually shipped it as part of the code, so you were getting the metadata twice, once for the 32-bit slice, once for the 64-bit slice. And now you actually get one copy of that either architecture can load in memory and operate on. And again, we've also made it more lazy. So what that means is now we actually don't load that metadata from the binary blob into the runtime memory until you actually use it. So the first time you hit a method or allocate a type or reference something of your reflection, we'll actually construct it for you, and you pay that price on use rather than upfront. So how do you go about profiling your IL2CPP code? So in our mind, IL2CPP first and foremost is a high-performance scripting VM for Unity. Second, and very close behind, it's also a .NET virtual machine. And what I mean by that is our main intent is that it'll run your code as fast as possible, and we're willing to make trade-offs when the need arises. But it also means that you can use general off-the-shelf .NET tools to do your profiling. Visual Studio, the latest version, ships with the profiler in it that you can use. You could also use any other third-party profilers like .trace or what else ships. And in general, any performance improvements you make in your code external to Unity, just as C# code itself or .NET code itself, those performance improvements will be reflected when you run it in Unity. After you've done your sort of general optimization, you can actually run it in Unity itself, in the editor, not necessarily on the device yet. And Unity has a profiler. We ship it for free from version 5 onward, and that gives you good insight into how is your code interacting with the Unity runtime. You may be doing physics simulations. You may be constructing things on the fly, instantiating objects. It'll give you an idea of how your code actually performs within the Unity environment rather than a generic .NET environment. And finally, after you've done these two other levels of profiling, you may deploy to a specific device and find out it doesn't have the exact same performance characteristics as you had in the editor or some other environment, and you may want to take a look on the specific device. As Josh mentioned, this is great now as we generate C++. So any sort of native profiling tools already support C++. It means you can basically load things up. For example, in iOS, you could use instruments and see the performance basically of Unity and the runtime, and also all your generated code will be there, easy for you to see in the instruments output. So let's take a look at an example. What we're going to do is take the MD5 crypto class here. We're going to allocate a megabyte of bytes. We're going to fill it with some random values, and then all we're going to do is compute the hash of that. So say, for example, you were streaming some content down from somewhere or loading some files off disk. You could do this checksum and calculate this in your application and make sure it was downloaded correctly. And what you're going to see is this is an interesting benchmark because without a CPP, we're not just converting your code. So IL2CPP is this general .NET runtime. We're converting your code. We're converting any assemblies that you may have in your project. And we're also converting all of the core class libraries from .NET. So the class libraries that we run with IL2CPP are the exact same ones that our version of Mono runs. We didn't rewrite them ourselves or change them. It actually is converting MS Core Lib and System Core and System XML right alongside of all your code. So what that means in this example is any changes in performance aren't just something you did, but it may speed up code, again, in Core Lib in this case, and run faster when you run it with the IL2CPP backend. And what we can see on an old iPod 4G is that our current version of Unity that we're shipping, compared to IL2CPP, you get a nice 25% speed up, just from basically processing the code generation via the C++ compiler, the Clang compiler from Xcode, rather than our previous Mono's code generation. So now you can basically send out tweets and tell everybody everything runs 25% faster. But we all know that's not the case, right? So it's interesting to see how different devices perform. So in this case, we're running the 32-bit code once again on an iPhone 6, which could run 64-bit code, but we're running the exact same binary. And what you'll see is there is a slight performance difference, but it hardly matters. You can't even see it on this graph here. And what that tells us is that different things obviously perform different depending on the device they're running on. So whether it's the fact that the memory bandwidth is a little bit wider on the iPhone 6, or it has a deeper pipeline for the CPU, it can execute these instructions maybe not as optimizedly generated, but it executes them just as fast as the previous code generation. Let's take a look at another example. I create this vector2 struct. It has two fields, an x and a y, two floating point values. And it has one helper method, this magnitude, to return the magnitude of those two components for us. And what we're going to do is we're going to allocate 1 million of these things in an array, and we're just going to run through and we want to sort them based on their magnitude. So we initialize the vectors based on I and the length of the array, zooming through it. And then what we're going to do is time it, and we call simply, again, the MS Core Lib helper method, array sort. You pass in the array you want to sort, and you pass in this case, an object that implements an interface. So you go out and you Google or you look at Stack Overflow, how do I sort an array? And you're going to get iCompare, right? That's the first hit that's going to come back. So we're going to implement this interface on our vector2 comparer class. It takes two objects, x and y in this case. We will extract out the vectors from there. We'll call getMagnitude on each one of those vectors, and then we do the proper calculations. We need to return something greater than 0 if the first is greater than the second, something less than 0 if the first is less than the second, and then 0 if they're equal. So we do this. We're going to skip all the other profilers, and we're going to go right to instruments. And what you can see here is at the top, there's two little things that help you when you're profiling. The second and third options that I have clicked are not clicked by default, and what that is invert call tree and also hide system libraries. And what that'll do is when you run instruments, it's going to bubble your script code to the top of where time's being spent. And what we can see here is that the most expensive, the most time-consuming call is actually in GC malloc atomic. So that GC does stand for garbage collector and gives us a good clue that we're actually allocating a whole bunch of memory. So if we go back real quick to our code, what we see is that's the two parameters there are object. And we know that objects are reference types. And we think, oh, you know what? As I'm whizzing through this array of 1 million items, every comparison operation is actually boxing those two vectors and doing a comparison. So we see that impact, obviously, is dwarfing anything else in our comparison run, the actual boxing and unboxing and creating these reference types through our comparison. So we do a little more Googling, a little more searching, and we see there's a generic version of iCompare. And with this generic version, it's strongly typed to the vector2 that we declared, and we see that the two parameters are no longer object, but vector2. And what that means is we won't actually box those value types before we do the comparison as we whiz through the array. The contents of the method are exactly the same as previous. And what we'll see is not only is the time run a lot faster, but now the most expensive, the most time-consuming method is actually our vector2 compare method that we wrote, which makes sense. That's what we're doing, is comparing every item in this array and ordering them. And you can see, running this iPod again, that by using the generic version versus the non-generic version, it's 2 to 3 times faster, just avoiding all these boxing and all these allocations that we were initially seeing. Now, when we do an array sort, what we had passed in before was an object that implemented an interface. The other thing you can pass in among all the overloads is a delegate. So we're going to declare some static methods, pass those in via delegate, and then the array sort routine is going to call these methods back. So here's our first one, compare vector 2. Again, it's strongly typed, so we don't have to worry about boxing. And we're going to take the magnitude of each, and again, the same logic to return that. So we look at this and we think, I'm pretty smart. I bet I can make this code faster. I'm going to inline that magnitude call, right? This is a hot spot. Why should I make a method call? I'm just going to do it myself. And I replace the contents of magnitude, math square root of the 2 components. And this is the results. So, of course, when we're optimizing, we make things slower. That's sometimes what happens. So what is going on here? Well, we can take a look at this. Here's the top is our compare vector, v2, our inline version. And the bottom, we can look at it and see the method that we actually inline, magnitude. Does anybody see anything jump out real quick? The var keyword kind of bit us here a little bit. What happens is we're actually missing the float cast from the return of the math square root. And what actually happened was that the C++ compiler is really smart. And when we generated the code before, we were actually doing the cast to a float value instead of a double. And it actually used a different instruction in the assembly code to do a 32-bit square root and 32-bit comparisons later on rather than the 64-bit. So by this accidental inlining, we actually were using actually more expensive instructions on the CPU than we could be. So once we fix this, we can actually see that the original method call, our incorrect inline call, and then inline fixed. The inline fixed does run slightly faster. It was 1 or 2%, I think. And finally, what we can think is, I don't even need to take the square root call, right? I'm just comparing the magnitudes, and we know that the components squared and summed together is actually a positive number. There's no reason for me to take the square root if I just want to sort these values. And what we can see is, when we don't do that, we get another little performance and benefit of what we're doing. And what we'll see here, this graph shows us a couple things we can take away from this. First is, if we look at the IL2CPP times, if we ignore the I comparable one where the GC basically dominated everything, what you see is no matter which one you pick, in IL2CPP you're going to be running faster than whichever one you picked with the previous scripting backend. So in general, across the board, you're getting a nice speed bump on everything. Another thing to pick out here is that the interface has different performance characteristics than the delegates. So we see in the first case, we run a lot faster. Each of the delegates were running 2, 3, multiple times faster. And then we see that I-comparable interface running only a little bit faster. And with a little bit of knowledge about the internals of IL2CPP, what I can tell you is we're not quite as efficient at dispatching interface calls as Mono is. So what happens here is I can tell you that even though we got some performance benefits in the math code, in the calculation code, we're a little bit slower in how we make interface calls currently. What that means, again, if you benchmarked all this, this was a hotspot for you, it might make more sense to do the delegate callback rather than implementing an interface on an object in this case. Again, I don't want this to be sort of general advice forever. This is just the current state of things. We're working to make it better. But what happens is when I profiled this yesterday and got these numbers, this gives you the state of things as it exists today. So 2 more quick things. Some of those are sort of general. I want to mention 2 things that are very IL2CPP specific, and you can keep in mind. One is, I mentioned before, IL2CPP for us is a high-performance scripting VM for Unity. And what that means is we're willing to sort of play fast and loose, fast and unsafe in some cases, to get the best performance for your code. So one of the things we have to do to be compliant with .NET is that we need to do null checks every time you access a reference object. So every time you load a field from something deriving from object, we need to make sure that it's not null. Or if you want to, for example, store something in an array, we do an array bounds check to make sure you're not writing past that memory. There's also things like divide by 0 checks that happen on integers. All these things to be compliant with the .NET standard, we do these things. But what we want to do is basically give you a way to control that. So in most of our opinions, we would say that null references are not something you want in a well-performing and proper game. So, we're thinking about giving you an option to add attributes to your assemblies, maybe an external config file to basically say, you know what, I wrote this code, there's not going to be any null references, please don't do any checks for me. And then we can remove those if checks from the generated code. Same thing for array bounds checks. We can say, you know what, I wrote this code, I'm deploying this to the device, I'd rather just crash rather than dealing with this performance hit from everywhere. I've tested my code, I'm sure it's working correctly. So we have that working internally. We need to actually get that into a release to you and document it the best way to do it. But we are thinking about how to make your code run as fast as possible. What we really want you to do is basically pay the cost for what you're using. So maybe, again, you bring a third-party assembly in. It's not written that great. They might actually write past the bounds of the array. You can say, you know what, leave array bounds checks on for this serializer DLL I'm using, but hey, in my code that's going to be really fast, I don't want to deal with that. Another thing with IL2CPP is there's a lot of places we need to do one-time initialization. There's a couple cases where we need to basically reference metadata. So what you can see in this magnitude example is I'm actually doing a debug log in there. So calling debug log in general is going to be slow. We don't want that in there. But the key here is we're actually using a string. So a string is actually a managed object, and that means it needs allocated by the garbage collector. So the first time we come into any method that uses a string, we actually call into the VM, that nice layer that Josh was showing. We ask it to, hey, please find the string that corresponds to this identifier, allocate it for me, and return it. And we actually cache it, so it's only done once. But what you'll see is in the prologue of any method using a string, or also any methods referencing metadata. So methods that do type of, or new up an object, or another case is basically static constructors. So before you reference static fields of any type, and you need to initialize those, the first time we have to actually call the static constructor for you. So again, we cache this, so it's only happening once, but the performance impact is it litters sort of if checks throughout the code. So it's something to be aware of. In general, we're seeing a nice performance boost everywhere, but it does give you the idea of, if you're doing some sort of math-intensive code, you may not want to be doing type of in there or allocating things. In general, if you're writing performant code, you're not going to hit these cases anyway, but it's something to be aware of that you may see in the generated code, and keep it in mind when you're writing areas that might be hotspots. One thing we want to say is thank you very much to you guys. We've been working out of CPP for a long time, and it's been a lot of community support. We thank you for all your bugs, all your forum feedback. It's really helped us make out of CPP into the success that we think it is.
Yeah, on a really personal level, for me and I think for John and probably our whole team, it's been great to see the amazing stuff that you guys are creating and is running on IL2CPP. That's really awesome for us, and so we thank you for that, and we're really looking forward to seeing what else you can create.
And with that, we'll take questions. There are 3
microphones
in the different areas. Yep.
Could we do the lights for the mics also, please?
Yeah. So, quick question: are you guys thinking about the extensibility of IL2CPP with future versions of .NET, like 2.0 to 3.5?
Yes. So IL2CPP is sort of a core part of our .NET upgrade. So the plan is basically to take IL2CPP to all of our platforms, and that's how we upgrade. So again, if we did a mono upgrade, it's not easy, right? It's basically we'd have to upgrade the mono VM to all those different platforms and port it to platforms that doesn't exist on today. So we run on generally more platforms than upstream mono does. So we'd be porting the AOT or JIT engine to each one of those platforms. So IL2CPP is our quick way to basically get to all the platforms, port it there, and then we upgrade, as Josh showed in that slide, we basically upgrade the VM code once. And all the platforms using IL2CPP are ready to go with a later version of .NET.
With respect to code generation, are you also thinking about caching some of the generation so it's not?
Yeah, so we actually have that out behind an environment variable right now. We're working, probably the most important thing to us right now, amongst many things, is build times. And we do work on a incremental build, and it's very simple. We basically generate the output to a backup folder, and then we diff what we generated previously to that, and we just copy this stuff over and leave it up to the build tools to just build what it needs. It's actually working, again, out there behind an environment variable. We do have some issues because what happens right now is our naming is not really stable. So we name, for example, C++ identifiers for all the strings, all the classes and types. And what happens is sometimes you can make a change to something, and it actually propagates to everything after it. So we want to make it as stable as possible so that a small change would just rebuild one C++ file instead of 50 or half of your files.
Yeah, so certainly watch the forums.
Yeah.
I mean, we'll try to release that stuff on the forums as much as we can once we get stuff out in patch releases, because and generally we're putting things out in all the versions, 4.6, 5.2 patch releases now. Everything's going out within a week, basically, of the time it goes into one release, it goes everywhere else. So we'll, especially for the build time stuff, we know that's a big deal, so we'll try to get information out about that as soon as we get the improvements in. And we're going to try to do that incrementally, pick up things as they go. So we're working on that. Thanks.
Do we get control over the compiler or linker options?
So we don't expose that right now. Well, for Xcode, it's just an Xcode project, and you can tweak the project however you want before you deploy. That's one of the actual considerations of porting is what does a build system look like for each one of these different platforms? Is it some sort of plug into Visual Studio? Is it a custom build script? So for WebGL, for example, we drive mscript in directly, and we expose some things, but you have much less control versus Xcode today, where it's just a project and you can do whatever you want to it before you build and deploy to your device.
So a productivity request. For people that use a lot of reflection, stripping can be a problem commonly. I'm hoping that you could add something in that reports what was stripped so that we could more quickly turn the important parts into a valid link XML file.
So
We could do that. I
Does
think
Jonas's stuff do that? The new stuff that he was talking about in the roadmap?
The old version of our stripper did have that information, I think, but we didn't actually bring it over. We could bring over information on what was stripped and why. The other thing we did recently, which is not what you want, but we can actually preserve whole assemblies now with like a wildcard. So if you are debugging this, instead of like iterating each type, you can just say preserve everything in this assembly, and I can do that.
The metrics would probably be nice to bring over.
But we can bring over metrics on what we took out and why.
If you're interested too, the manual page online for the link.xml and iOS like build size stuff, we just rewrote a lot of that with some new information about the features in the IL2CPP stripper. So if you haven't looked recently, I think it just went up with a 5.2 doc. So.
Okay, yeah, I mean, the main thing is just getting all the names that were stripped so that you don't have to hunt them all down.
Yeah.
One other thing that might be really useful would be if you could mark a namespace for not being stripped.
That's possible now.
That's possible?
Okay,
that's
yeah, so take a look at that. I think there's an example of that now in the new manual page docs. So take a look at it. If not, stop by our scripting table, and we'll show you how to do that, but it's definitely possible for namespace level.
Just a quick follow-on to that. So like in an editor, like if you turn off the stripping, like it still actually does stripping for WebGL stuff. I think it'd actually be useful to like still be able to do not stripping and like for these kind of debugging scenarios to verify everything's working and then turn it off obviously for your production stuff.
So that's accessible through the link XML now. And that's one of the newer things we've added. You can actually say in link XML on the assembly element, you can say preserve all, and that'll turn off stripping on an assembly. So it's not quite the same as disabling it totally, but
in general, we'd like to fix any bugs that exist with stripping rather than turning it off. Because I mean, for a target like WebGL, we really need it to actually run. I mean, even for debugging purposes, the code we're generating might be just too large to load in many browsers.
yeah, and I think in 5.1, maybe in 5.2, but certainly the GUI in the editor is better now, right? We used to have like stripping disabled and it would still strip, which was just what? I mean. That's bad. So now I think they switched. There's a checkbox that's like strip engine code or not, it's a totally different thing. So it's a little bit better, and I think maybe that's in 5.1. I think I'm not sure if it's in 5.1 or 5.2, but the editor looks a little better. But if you're still using 4.6, you've got the weird like stripping disabled, but we still strip. So sorry.
Sorry, one more question. So can you speak to the WebGL stuff at all? Like, are you guys getting like a lot of big gains recently with 5.2 for WebGL size, performance, anything?
There's a WebGL talk going on right now.
Unfortunately.
And I don't want to speak to that.
same time,
you,
yeah.
you have to talk to the WebGL team at the Ask the Experts. That'd be the best thing to do.
Yeah, sorry, we don't know about that.
Any other questions?
Yeah. Could you go to the mic, please? Do you mind? Sorry. For the people who might be listening in the future.
Is there a point at which you'll stop supporting Unity 4 with this?
Yes.
When is that point?
The Unity 4 patch releases are stopping, I believe, the end of this year. We had a blog post by our sustained engineering team. That's not so much our specific decision, that's more sustained engineering. But as long as we have 4.6 patch releases, we will continue to support it with IL2CPP. So we're never going to have a different version of IL2CPP on 4.6 than we do on whatever 5.2 is on. So we're going to continue doing that until the 4.6 patch releases stop. And I know there's some maybe caveats in there, information about if there's like a serious issue, they'll continue to patch 4.6. But
you should
yeah.
take a look at the blog post.
Yeah, there's a blog post that details, if you haven't seen that, what our sustained engineering team is going to do. But from our perspective, we're going to continue to backport all the changes for IL2CPP.
Okay.
Kind of got things set up in our development environment to do that relatively easily.
Okay, thanks.
No, that's a big deal for people.
Yep.
So as C# scripters, we'd like to know that if we're writing the most optimized C# code, that when it comes down to the C++ level, that it'll be optimized as well. And I know that you're trying to do everything to make sure that happens, but you showed a case where there are some times where it may not be intuitive, that it's not optimized the same way. Do you have a list of those gotchas, and do you have a way of being able to get those
No,
to
I mean, that's really
developers?
kind of what I don't want to do. Like, I don't want to make this list because, again, it varies a lot on device and how things expand. I mean, in that case, it was clear in C#. Basically, we were doing 64-bit math instead of 32-bit math. It's just that the var keyword sort of hid that. But in general, if my best advice is to profile, basically profile at all different levels. And other than sort of super generic advice, it's really hard to make any sort of absolute statements of if you do this, you'll get uniform, better in performance across the board.
Yeah, as we saw like with the iPod fourth generation versus iPhone 6, I mean, it's really amazing when you go to some of the newer devices especially. I mean, it's really different from what you may have experienced in the past. So it's hard to profile on all your devices sometimes, but.
Yep.
What's it like debugging calls that go across the managed to native boundary? Is that all like the trampolini kind of stuff?
No.
Does that still exist?
No, that doesn't exist in IL2CPP. So it's really just like as good as you saw me debugging here on stage, which is not to say great, but better than you got with trampolines.
Okay.
And like I said, all the marshalling directives you write, like if you have a DLL import and private extern, and you write marshal as LP stir or marshal as fixed or size array, all that stuff we translate those marshalling directives into generated code. So you can actually see kind of how we're allocating the array. You can see where we're allocating the strings, where we're making a copy from like the UTF-16 string to a UTF-8 to pass as a char star, WCHAR-T, whatever it happens to be. So it's the same debugging experience you get with generated code. So it's better than trampolines, but not great.
One of the things I wanted to say was that the generated code is not like, we're not comparing the generated code to your C#. We're comparing the generated C++ code basically to the assembly we outputted from Mono beforehand. So again, this is not something we want you to look at in the sense that nobody looked at the assembly code we generated before. It's just that we generate C++ now, and some people say, hey, I can read that, right? So for us, this is good because instead of generating machine-specific assembly code, we're debugging C++ that we output. So remember, the analogy here is that C++ code we're generating is the assembly code we had before, not, we want you to debug this rather than the script you're writing today.
So C++ with gotos are okay, I guess, in that respect.
So I noticed at one point, like when I was changing from the scripting backends, like IL2CPP back to the Mono, like the stripping stuff was actually different. Like it was stripping some things differently. Can you kind of explain like how the stripping works now? Like you're not stripping the Mono before you do the generation. You're doing it like some different.
Yeah. So we basically had a stripping tool before, and we have a new one that's based off that, but we made it better in our minds. The code was a little convoluted before, and we really wanted to get we wanted to remove as much as possible because WebGL was sort of our first platform for IL2CPP, and it was super sensitive to size. So everything we could strip out of there to run in the browser was a big win for us. So it is actually running two different tools to strip, when you choose the Mono backend versus the IL2CPP backend.
Okay.
All right.
Like I said, thank you guys very much.
One more.
Sorry. Apologies.
I know that Unity 5.2 has experimental Android support.
Mm-hmm.
Do you have any insights like compile time and crashes?
So Android's going to be a little bit different. So before, so iOS was always an AOT platform, for example. So you had a little bit longer build times, whereas Android was a JIT platform before. So you're going to see, obviously, a little bit longer build times. The other thing you'll see is maybe AOT issues. So most people were targeting both mobile platforms, and you were aware of sort of AOT issues when you were on iOS. But if you just had targeted Android before, you may have to basically deal what you would have dealt with putting to iOS before, which is any code generation, sort of runtime serialization stuff might trigger basically exceptions because we can't generate code on the device.
Yeah, I don't think we've seen any real-world bugs yet from Android, but the platform teams do deal with a lot of that as well, so we don't always see those.
One more. What if we obfuscate our C# like managed code?
So that's one thing that we did not do intentionally, but everybody asks about. So with IL2CPP, we don't ship your assemblies anymore. So we actually, during the conversion, we extract everything we need, and we basically throw your assemblies away. And all your shipping is basically, C++ code that's compiled and a compressed, compacted binary file of the metadata. So for those of you worried about sort of reverse engineering or someone looking at your assemblies downloaded, you're not actually shipping your assemblies anymore.
But we can convert obfuscated code with no problems. We can handle Unicode characters in IL. That was a fun bug. And I didn't fix it. But yeah, that was an exciting one. Yeah, so we can convert obfuscated code as well.
All right, I think that's it. Thank you guys.
Thank you guys very much. We appreciate your time.